This video is to help you with your write-up for tutorial 6. In an earlier tutorial, we visualized the age differences between actors and actresses who would win an Academy Award. But we were looking at the whole population then. In tutorial 6, we took a small random sample to mimic what we would do in most research situations where we don't have access to the whole population. We took 25 random actresses and their ages, and 25 random actors and their ages. And we can average the ages in each group to get a sample mean. And this serves as an estimate of the population mean. We see even in our small sample, the average age of female winners is lower than the average age of male winners. And this is consistent with what we saw in the population. Your sample is probably different than mine, and they're both probably different than what we saw in the tutorial. And that's good. Each of them is random. They should be different. Before, when we wanted to display the difference between two means, we just plotted the averages as columns. But from now on, we need to include a measure of variability on the graph. And this allows the reader to see not only the difference between the two group means, but also how much the ages in the sample vary around each of these means. And we can do that with error bars. In the text, we use standard deviation, but on graphs, we're going to use the standard error. A simple way to remember that is if you're using error bars, you need to use the standard error, not the standard deviation. Standard error is similar to standard deviation, but instead of how much the data points in the sample vary, standard error is the amount of error or the range of the possible mean we can expect given a sample of a certain size and variability. Excel will calculate the standard deviation for us, but we need to write out our own formula for standard error, which I've already calculated. The formula for that is the standard deviation divided by the square root, and that's SQRT, of the sample size. To add the error bars, we will go to chart design and add a chart element. This is where we can add a lot of different things. We're going to go to the more error bars option. And we want to choose custom. I know it says standard error right there, but don't let Excel put in error bars for you. It's making a guess, and Excel is usually good at guessing, but for standard error and error bars, it's almost always guessing incorrectly. So we are going to add it via custom. So the positive error value and the negative error value should be exactly the same. The way that we calculate standard deviation and standard error is to see in both positive and negative directions around the mean how much variance is there. So to do that, we're going to grab both the actresses and the actors for the positive, and again, the actresses and the actors for the negative. Okay, those are pretty small, and as you can see, it's a lot smaller. The standard error is a lot smaller than the standard deviation. So let's make this chart look a little nicer. I'm gonna have my title all fit on one line. This is a small amount of variability, so let's make these a little longer. And I'm tired of always having blue, so let's just pick a different color. I personally like teal, so we're gonna put that in. Okay, let's put that in our write-up. Copy, paste that in there. Again, I'm gonna change this to a picture. It's just easier to move around and make sure that my proportions don't get screwed up. We can now do a comparison of the means. We have one categorical predictor variable, gender, and one continuous outcome variable, which is age. In the tutorial, we calculated the t-value for you based on the mean and the standard deviation of each sample group. So here's how you would report a statistically significant difference. When it comes to the age at which actors and actresses win an Academy Award, there is a statistically significant difference between the genders. And then we report the findings from our inferential statistics test, in this case t-test. We include the p-value, which in this case is much less than 0.05, and that makes us think this is a true difference. These groups are truly different from one another. We also want to include the actual mean and standard deviation for each group and tell the reader what it is that we found. So females win the award at a younger age than men. Until you learn how to calculate these in a statistics course, reporting the mean and the standard deviation with some tentative interpretations is acceptable. A good way to visually evaluate the difference in means is to make sure that the error bars don't overlap. If standard error means that the true population mean is likely to be within that range, we can feel a little more confident if the ranges don't include the same value. So if I got 41, that's not a possible, that's not a probable population mean for actors. Without the results of a statistical test, you cannot use the word significant in your write-ups. That is a code word for researchers that you have done those calculations. So if you use the word significant, you must include the results of a significance test. So let's pretend that I haven't done the t-test and I don't know whether or not it's significant. Without those results, I must take out this statistically significant part. So what I could say is when it comes to the age at which actors and actresses win an Academy Award, there appears to be a difference between the genders. And again, I still want to report, on average, they win it at a younger age than men, and include this mean and standard deviation for both samples. Let's move on to the next visualization that we did in the tutorial. For this part of the tutorial, we ignored the continuous outcome variable of age and just wanted to go back and look at how two categorical predictor variables make up a group. In this case, the group is the whole population of winners. I have two different options for visualizing these proportions. I can give each subgroup, males with light hair, females with red hair, their own column to represent the proportion. That's perfectly accurate. But also, because this is a part-to-whole relationship, with light hair being part and all male winners being the whole, I can also choose a stacked 100% column. So how do I choose? Well, what questions do I want to ask about these data? Maybe I want to know whether hair color predicts winning differently in men and women. With these two categorical variables, I want to know if the pattern of hair color in men is the same as the pattern of hair color in female winners. Or, because I have a 50-50 split between men and women, is there a 50-50 split of men and women in each of the hair color groups? In this case, a stacked column may make it easier for me to see any differences in the patterns, whereas here I would need to compare both within this group and across the different levels of gender. So I'm going to choose a stacked column. So let's put this in our write-up. So what do we notice about these frequencies? Are there any differences? The most obvious thing to note is that while redheads make up about 20% of the female winners, there are no male redheaded winners. So let's write a sentence about that. Make up about 20% of female winners, there are no male redheads who have won. What else do we see? The proportion of light-haired winners is about the same for men and women, but the proportion of dark-haired men is much larger than the proportion of dark-haired women. So let's also put that into our write-up. The proportion of light-haired winners is similar for men and women, but the proportion of dark-haired men is much larger than the proportion of dark-haired women. So that's what we just said. But wait, I've just jumped right into my multivariate relationship without saying anything about main effects. We already know that there's an equal number of male and female winners in the population, but what about in hair color? We can add a sentence or two about that. Instead of breaking it up by male and female, I can just look at the proportions within the whole population. So it looks like there's a larger proportion of dark-haired winners than light-haired winners, and there's very few red-haired winners. So let's say something about that. We don't necessarily need a graph for this. We can say that it appears hair color is predicting the winners within the whole group. And then we can report the exact amounts, especially because we're not going to include a visualization. So over 50% have dark hair, very few have red hair, and this 34% have light hair. This is different than what we just said about our male and female winners. So let's point that important fact out to our reader. This pattern that we just reported, this main effect, is not apparent in both genders. So let's point that out to our reader. This pattern is not the same for men and women who win the award, suggesting that the effect of hair color depends on gender. Okay, at this point, are there any other interpretations that I can make? Can I say something like, brown-haired women are better actresses than red-haired women? Or, the Academy is biased against red-haired men? No, I would need to do additional causal studies, and right now I can only interpret the details of the current winners. The proper way to test whether these patterns are different than what we would expect is called the chi-square test. We're not going to calculate that inferential statistic, and we're not going to include the results of that test in the write-up, so we can't use the term significant anywhere in this interpretation or part of the write-up.